Hey guys, welcome to another IGCSE physics revision video. Today we're going to be covering the second part of electrical quantity. So I have a quick look at the syllabus and we will begin the video. I will try to keep the video at a sort of short-ish length. I do realize that the videos have been getting progressively longer, but it does seem that physics is a bit longer per topic than chemistry and biology, and that's sort of one of the reasons why it takes longer. Also, I think the concepts are a bit harder to describe or explain with physics than the other sciences, but I will try and do my best to keep it short. So the first thing we're going to be looking at is current, which is basically the rate of flow of charge. The equation for current is I for current measured or units for in amps, Q is charge, which is coulombs, and time for seconds. And so in metals, generally, current is due to the flow of electrons, and you should already be aware of that by now. And so this is sort of the counterintuitive thing that you do need to realize. The direction of conventional current is always opposite to the direction of electron flow. So if you take a look at this example on the right hand side here, you've got the positive terminal up at the top and the negative terminal down at the bottom for this battery. So electrons being negative will always move from negative to positive, therefore going in this anti-clockwise fashion. Conventional current, despite the fact that the electron flow is causing the current, the direction is opposite, which is sort of, it makes no sense. But the reason for that is because initially when they first defined current, they defined it as a rate of flow of positive charge. And so they only really realized afterwards that electrons were negatively charged and they flowed in the complete opposite direction, but they decided not to change it and decided to keep the definition of conventional current being the flow of positive charge. So therefore, because electrons are negative, the electron flow will always happen, from negative to positive, just like this right-hand side diagram here, but the current is flowing in the opposite direction because by definition, current is the flow of positive charge. But I don't really think that matters. For your sake, for your course, all you need to know is that electrons flow and the conventional current is always going in the direction that is opposite to the electron flow, and current is defined as the rate of flow of charge, and you have this formula up at the top that you need to learn. Now, this concept here is a fairly difficult one to explain, but electromotive force is basically an electrical supply, right? So if you think about a power pack or a cell or a battery or whatever it might be, those are all electrical supplies, and those provide electrical energy which drives charge around a complete circuit. So the charge gains electrical energy from the supply. So by definition, the electromotive force of a supply is the energy provided per coulomb of charge and is measured in volts. The formula here is EMF, which is V, is work or energy divided by the charge, which is in coulombs. And so EMF is always to do with the supply of electrical energy. So it's always to do with whatever is providing the electrical energy for the circuit. It could be a power pack or a cell or a battery, whatever it might be. EMF is to do with that. So to put it simply, right, so think about a battery, right? A battery converts chemical energy into electrical energy, which is then supplied to the charge that flows around the circuit. And so if a battery has 9 volts, a 9-volt battery, what that essentially means is that the battery supplies 9 joules of energy per coulomb of charge, which basically allows it to drive the charge around the circuit. And so that is electromotive force. But oppositely, potential difference is the amount of energy required per coulomb of charge to drive the current through a specific component. So whilst electromotive force was dealing with the amount of energy supplied to charge at a supply unit, for example a battery, the potential difference is mainly to do with how much energy is required to pass current through a certain component. right? So the component could be like a resistor or a light bulb in this case, or whatever it may be. It's to do with the components in the circuit rather than the supply. So in other words, to put it simply, it could also mean that the potential difference or the voltage across a certain component is the amount of electrical energy that is converted into other forms, for example light in a light bulb, per coulomb of charge. And this is just like EMF measured in volts. The formula is exactly the same. The only difference really is that work or the energy in when we're dealing with EMF is the energy that is supplied, but in this case when we're dealing with potential difference, it is the energy that is sort of lost or converted into other forms from electrical energy. So if you take a look at this diagram to the right here, let's take a look at this bulb. Now the bulb will convert electrical energy into light energy, right? So a 1 volt lamp, what it means is that 1 joule of electrical energy is basically converted into light energy per coulomb of charge. And in other words, it also means that 1 joule of energy per coulomb of charge is required to drive the current through this particular light bulb. So whilst EMF and potential difference are very similar, they are sort of the opposite. Again, remember, EMF is to do with the supply, how much energy is being supplied to charge, and the potential difference is how much charge is being converted sort of from electrical energy to other sources of energy, or other energy like light energy and things like that. And so it's pretty important to understand the difference. The next thing we're going to be looking at is resistance. The electrical resistance of an object is a measure of its opposition to the flow of electrical current. Resistance is measured in ohms, and it's got this unit over here. And so the formula that you have to know for resistance is that resistance equals potential difference divided by the current. And potential difference is of course measured in volts, and current is measured in amps. Now to measure the voltage of something, or the potential difference, we use a voltmeter, which has this component diagram here. And to measure the current of something, we use an amp meter, which is which has a component diagram like this. But we will be learning a bit more about that in the next topic. But for now, just keep in mind that a voltmeter measures voltage and an ammeter measures the current. And so if we had an unknown resistor for which we don't know what the resistance is, how can we find out the resistance of that unknown resistor? So we've got the resistor in this circuit over here, like so, and if we were to sort of connect the voltmeter basically tells us how much potential difference is going across the resistor here. We've got the ammeter connected as well. The ammeter will tell us how much current is flowing through the circuit. Now if we were to close this switch and connect the circuit all together, what we'll find is the voltmeter will give us a reading of the potential difference, and the ammeter will give us a reading of the current that's flowing through. So if you were to put that into the formula, R equals V divided by R, immediately we get the answer for what the resistance of this unknown resistor would be. So for example, if voltage was 4 and the current was 2, then 4 divided by 2 would give you 2 ohms for this unknown resistor. Now, the method that we used before, we are only working with one set of readings. We just connect everything up and we get one result for what the voltage might be and one result for what the current might be. We divide those together and we get the resistance. But there might be a better way to do this, right? If we wanted a more accurate set of results, we would sort of ideally want multiple measurements and then divide all of them, or sort of average the results to give us the most reliable, true resistance of the unknown resistor. So instead of connecting it like the way we did before, what we're going to put in is everything else stay the same except for the addition of the variable resistor, which is basically a resistor that has known resistance that can be altered, right? You can alter it from 1 ohms to 2 ohms to 3 ohms to 4 ohms, depending on what the range might be. We know what the resistance is and we can alter it. That's the main idea behind a variable resistor. The important thing about the variable resistor in this particular setup is because as we change the value of the variable resistor, say we go from 1 ohm to 2 ohm or 2 ohm to 3 ohm, every time we change that, it's going to change the reading on the ammeter and it's going to change the reading of the voltmeter, which means that the current flowing through the circuit changes and the voltage going across the unknown resistor will also change as we change the resistance on the variable resistor. What that means is we can get a couple of results, right? So let's just say we set the variable resistor to 1 ohm. We'll get a certain reading for the ammeter, we can get a certain reading for the voltmeter. So V divided by I will give you the resistance for that unknown resistor at that particular point when we set the resistance to 1 ohms. Now what if we change the resistance to 2 ohms? Again, that will change the resistance on the that'll change the reading on the ammeter and it'll change the reading on the voltmeter, and that means we can apply the formula again, V divided by I, or voltage divided by current, and you'll get another calculation for what the resistance of this unknown resistor might be. Obviously, the results will be very similar, but they may be slightly different, which is why we are doing this to begin with. So you can do that multiple times. We can change the resistance from maybe 2 ohms to 3 ohms and then calculate V divided by current or voltage divided by current again. And so we can get around 5, let's just say we get 5 different very similar values for the resistance, and then you can average the results, and that will be a more accurate result than just applying with this setup here. We just get one set of reading for one reading for the ammeter and one reading for the voltage, and then just calculate resistance from that. Rather, we can get multiple sets of results and average it all together and then calculate what the resistance might be, and that will be a bit more accurate. And so the important thing about circuits is that all these components, for example, this resistor, this variable resistor, and the ammeter here, and the battery, these are all connected by wires. So it would make sense to talk about the resistance of a wire. The resistance of a wire depends on two main things. We've got the length of the wire and we've got the area of the wire. Now, if you think about this logically, it actually makes a lot of sense. When the length of the wire is basically increased, the current has more to travel through, right? It has to travel further in the wire, and therefore the resistance will increase, right? There's more sort of, if we take a look at the definition of a resistance, remember, it's the measure of its opposition to the flow of electric current. So if the current has to travel more, then the opposition increases. Therefore, as the length increases inside a wire, the higher the resistance. Oppositely, when the cross-sectional area of a wire is increased, for example, if you increase the diameter, the current has a greater area to travel through, so therefore it has to work less to go through the wire, therefore the resistance decreases. So these relations are really important. As the length of the wire increases, the increase in resistance, and as the area of the wire increases, the decrease of resistance is what you'll find in terms of these relationships. And finally, what we'll be looking at is electrical working. Electrical energy, as we described before, is basically transferred from the battery or power supply in a circuit to the components in the circuit through electrons. So charge basically gains energy from the supply. And components, in turn, will convert the electrical energy from the charge into other forms. For example, the electrical energy carried by the current will be converted into light energy inside a light bulb. And so the rate at which energy is transformed is called power, and power can be calculated using the formula below. We've got potential difference multiplied by current, which gives you power. Okay, and so basically power has the units of watts, and that's quite important. So in short, P equals VI. Now, energy is calculated by timesing power with time. So if power is voltage times current, VI for short, then what we can say is energy equals voltage times current times time, times time. So these two equations are quite important. Now, we've talked about a few different things in this video today, and we have a couple of equations that we went through, and a lot of the questions that they give you is based on calculations. So the next video I might just go through a couple of example calculations to go through how to calculate current, voltage, and work, energy, things like that. So look forward to the next video. We'll go through that together. But that sort of does cover most of the fundamentals of this topic, so please like, share, and subscribe. Please consider joining Patreon for past paper tutorials and other things. Haven't uploaded any physics ones yet, but I have done a couple of IGCSE biology and chemistry, so if you're interested, please think about that. Otherwise, I will see you in the next video.